talking about the intermittency of velocity circulation in quantum turbulence. So please, when you're ready, Nicolás, take it away.
Okay, thank you, Andrew. So hi, everyone. First of all, I would like to thank the organizers for letting me present my work here today. So I will present myself first. I'm Nicolás Müller. I'm a PhD student at the Observatoire de la Côte d'Azur in France. And well, I will talk about the intermittency of velocity circulation in quantum turbulence. So first of all, the work I will present today here has been done together with George Kristlovich, who is my supervisor, and also with Juan Polanco Arnacho, who was a postdoc here and now is doing another postdoc at the École Centrale de Lyon. And the results I will show today were published in two different papers, one PRV and one PRX. And today I will focus more on this second one, which is the one that is related with circulation. So, well, to start with, what is a superfluid? Superfluid is a particular kind of fluid that has no viscosity. So that means that it can flow freely with no friction. And the second main property that it has is that the vorticity is concentrated along vortex filaments with that are topological defects with a quantized circulation. So some examples of superfluids are Bose-Einstein condensates, liquid helium, light in nonlinear media, and in the core of neutron stars. And all these systems present different critical temperatures below which a superfluid takes place. So here on the right, I show you a visualization of the superfluid that was done by Dan Lathrup's lab in Maryland of liquid helium. And yes, you can see how is the interaction between these quantum vortices. So what is the main difference between classical and quantum vortices? Well, I like to say that there are two main differences. One of them is that the core size of a quantum vortex is something that is very well defined and is given by the healing length psi. While on the other hand, it's very hard to define a size for every vortex in classical turbulence, in classical fluids. And the second main difference is that if you compute the circulation of a classical vortex, which is basically the definition is the integral line within a certain closed loop, it can take any continuous value. While on the other hand, in a quantum vortex, it can take a quantized, a discrete value that is multiple of a value kappa, which depends only on the properties of the flow. So in principle, there are many models that we can use to describe the dynamics of superfluids that take into account the different temperature regimes or different length scales. In particular, today we'll talk more about the Gross-Pitaevsky equation, which is a mean field model for weakly interacting bosons at 0 temperature. So we can describe that as a superfluid by a macroscopic wave function of the condensate, which follows the Gross-Pitaevsky equation, which is no more than basically a Schrödinger equation plus a nonlinear term. So it is also known that we can use the Madelung transformation to relate some hydrodynamical properties. We can relate the macroscopic wave function with some hydrodynamical properties of the fluid, like for example, the mass density or the velocity field, and also by plugging this transformation in the Gross-Pitaevsky equation, it is possible to recover the continuity and Euler equation, that are equations for a compressible flow with no viscosity. So basically in superfluids and in particular in helium, there are 3 different length scales that are very important for its dynamics. At large scales, we have the integral length scale, which is usually associated with the size of the system. and which today the largest experiment with liquid helium is the Shrek experiment at Grenoble, which is of the order of a meter. Then we have at intermediate length scales the intervortex distance, which is of the order of typically of the order of 10 to the minus 5 meters. And the smallest length scale that we have in a superfluid is the vortex core size, which is of the order of an Armstrong. So we can see that between the largest and the smallest scale, there are almost 10 decades of difference, which is a lot, and is what makes some studies of turbulence and the and doing numerical simulations so hard. And also when we study quantum turbulence, which is basically the turbulence that takes place in a superfluid, we know that at large scales, between the integral length scales and the intervortex distance, there is a Kolmogorov cascade that takes place, which is basically a semi-classical behavior because it also takes place in classical fluids. While on the other, and in this regime, there's energy that is transferred from largest to smaller scales up to here. And then we have another different cascade, which is a Kelvin wave cascade, which is basically correspond to the waves that propagate along vortex lines. So basically a little reminder about what is Kolmogorov turbulence. So we know that we can define the velocity increments like this, like the difference between the velocity field at 2 different points. And by doing numerical dimensional analysis, we can find how is the scaling of these velocity increments as a function of the energy dissipation rate that has these units and the some increment. So, and we can obtain that the velocity increments to the square scale as epsilon to 2/3 and r to the 2/3. And from this, we can obtain a scaling for the energy spectrum that goes as with that scales with the wave number as k to the minus 5/3 within the largest scales of the system. So this is known as Kolmogorov scaling for the energy spectrum, and this is something that is very well established and it is something very well known that takes place in superfluids because it has been seen in observing experiments and numerical simulations in the Grosby-Tversky equation and in the vortex filament model. So today, I will show you some numerical simulations that were performed in a generalized Grosby-Tversky model. So what is this? Basically, a generalized shifting model is a shifting model that involves a non-local potential between the bosons, and also a high-order nonlinear term to take into account stronger interactions between the bosons. Why we wanted to do this? Well, because by choosing the right interaction potential, we can somehow reproduce the Rotom minimum in the excitation spectrum and find a model that is somehow closer to liquid helium. So yes, now I will show you a numerical simulation of this system. The red lines correspond to quantum vortices and the greenish rendering to density fluctuations or sound. And you can see that as it evolves, vortices start to interact within themselves. They reconnect and sound is emitted. You can see how a turbulent flow is developed. So from this system, we can measure different things, like, for example, the energy spectrum. And we observe that we can observe a simultaneous, we obtain a simultaneous observation of 2 cascades. At large scales, we observe the Kolmogorov cascade that goes as k to the minus 5/3, while at smaller scales, we observe this Kelvin wave cascade that again also follows k to the minus 5/3. at intermediate scales, we see a plateau that is given by the intervortex distance. So yes, so this is something that was published in this PRP paper. And we also discuss how is the scaling with different prep factors, like the energy dissipation rate and other quantities of interest. So going back to the circulation, so we have that in a superfluid, we can have a vortex with a positive or a negative polarization. Now let's consider that kappa is equal to 1, only to simplify. So if we compute the circulation around a closed loop that contains a vortex, we can measure how strong is the rotation, the local rotation of the fluid. So here in this case, we have only one vortex, so we have that the circulation is 1. If we add more vortices, here we have 2 positive vortices, 1 negative vortex. We have that the total circulation here is 1, and so on. So in this way, we can measure the local rotation of the system. So and this is what we wanted to do in a numerical simulation. So we performed a 2000 cube direct numerical simulation of a decay in ABC flow. So this is a visualization of the system. Here there are some scales that of the system. And on the left, I show you a visualization of the vorticity of a 2D slice of the vorticity, where the red and the blue dots correspond to positive and negative vortices. And what we did was to study the circulation of the system with different loop sizes. So for example, for a certain loop size, we compute the circulation at every point of the system in this 2D slice, and in every possible slice, in every possible orientation. So by doing this, we can obtain for each loop size different probability distributions, which I show here. So here on the top panel, I show you the probability distributions of the circulation for small loop sizes. So that is loop size is smaller than the intervortex distance. And here the light histograms correspond to smaller loops and the dark to larger ones. And we can see 2 main things here. The first of them is that the discreteness of circulation is evident, so it takes only integer values. And on the other hand, the loop size becomes larger, it can take larger values because it can contain more vortices. On the other hand, at large scales, we obtain different probability distributions where we can see that maybe the discreteness of the circulation becomes maybe less and less relevant. I mean, the circulation is still discrete, but it starts looking more like a continuous distribution. So from these probability distributions, we can measure, for example, the different moments of them. And for example, we can compute the circulation variance of the system. So by doing, again, like in Kolmogorov 41, if you do numeric dimensional analysis with the circulation, we can obtain a different scaling for the variance that goes as the area to the fourth, the area of the loop, right? And this is something that has been done 2 years ago by Pierre et al. in Navier-Stokes, that is in classical turbulence, in very high resolution numerical simulations of classical turbulence. Here they observed indeed this scaling. Here is a to the 2/3 because it's actually the square root of the variance. But basically they observed this scaling in a very wide range of scales. And this is what we also did, but now in quantum turbulence. So the main thing that we observe here is that there are 2 different scales. Sorry, 2 different scalings. At large scales, which is this green region, we observe this Kolmogorov scaling, while on the other hand, at small scales, we observe a different scaling that is linear with the area, which is basically this is a trivial scaling because it is the scaling of a single vortex. So this is important that this is a trivial scaling. But the important thing here, which I want to focus on, is the large scale, because again, we recover a scaling that is the same that we observe in classical turbulence. So here I show you again some results in classical turbulence. We observe the same scaling. This is very interesting because we know that the nature of vortices is very different in these two cases, but we are able to obtain the same scaling. On the other hand, here at small scales, we obtain a very different scaling because here the different nature of vortices is indeed relevant. So just a comment here. We also compare this simulation with a standard GP simulation in quantum turbulence, just to see that the scaling is the same. This is a low resolution simulation, so but there's actually no. This is what we expected to find exactly the same behavior in both systems. So, and just to say something else, we can also study high order moments of the circulation, and we can study how is the intermittency of the system. So what do I mean with intermittency? Well, I mean deviations from the Kolmogorov scaling for high order moments. So we know that by doing this dimensional analysis, we can obtain a scaling that is given by similar as in Kolmogorov 41 for the circulation that goes as the linear loop size R to the 4p third, right? So, but this is something that doesn't happen for every p. So in general, we want to write the scaling of the different moments of the variance as lambda p, with lambda p would be smaller or equal than the Kolmogorov prediction. So here on the right, I show you how these different moments for different p's, with the lighter one correspond to a small p and the darker one to a larger one. And we see different scalings. So the first observation is that at small scales, they all display the same behavior. And this is again because here this is a trivial scaling of the system. We have only 0 or 1 vortex. So yes, we will expect the same scaling for every p. While here we have different scalings. So if we compute, for example, the local slope of the system, which is the logarithmic derivative of this, we can obtain how is this slope, or basically how's the scaling of the system. So if we have a flat zone here, we have a power law here. And we observe that as p is larger, there are some deviations from Kolmogorov predictions. So this result can be summarized in this anomalous exponents figure, where we show how is lambda p, the scaling exponents, as a function of p. And we observe that indeed, as p becomes larger, the deviations from Kolmogorov prediction becomes larger. And what is even more important is that the intermittency of this system in the intermittency of quantum turbulence for the velocity circulation follows the same behavior as in classical turbulence, which in ER et al. They show that it can be fit by a bifractal fit in classical turbulence. So this is to show that it follows the same behavior as in classical turbulence. So that's it. so basically here are the conclusions. So so thank you for your attention, and so if you have any question.
Thanks very much, Nicolás, for a very interesting talk. If anyone's got any questions, either use the sort of raise your hand. Yeah, Yuri. Or you're muted at the moment, Yuri. Or if you've got questions, either do that or pop them in the chat.
Yeah, right. You can hear me now.
Yes.
Yep.
Nicolás, that's more about the first part of your talk. I understand that there is in some way you can identify the sort of existence of bundles, right, of vortices. And so I wonder, well, and people talk a lot about that because they, after all, determine the Kolmogorov nature of spectrum and these sort of things. I wonder whether there is any way of finding the typical size of the bundle and its lifetime, for example, or perhaps some statistical properties that would directly tell us.
Yes, for example, I think that for example, in this bifractal here that they showed in Year et al., they assume that in this second range, the fractal dimension of the system is like 2.2. So this fractal dimension of the system is associated maybe with some vortex sheets or some maybe vortex bundles. Mm-hmm. So this is a way, I think, that to measure that the presence of vortex bundles. And also, I don't know if it's, well, probably it's possible to measure the lifetime of these bundles. But I mean, I think yes, it could be possible to study how the dynamics of these individual vortices as a function of time and find different statistical properties. Because once you do this, you will have a system that is basically discrete, so you can yes, easily study the dynamics of these single vortices.
Mm-hmm. Okay, thank you.
Welcome.
So Makoto, you've got your hand raised.
Yes, so thank you very much for a nice talk. I'm Makoto Tsuboda from Japan. I'm interested in the difference between the generalized GP and the traditional usual GP. You made both simulation, right? And you found no difference in the spectrum of circulation. Did you find any difference between them? With the usual energy spectrum or something like that?
I mean, yes, actually, this is what I showed here before. For the energy spectrum, there is a difference between the generalized and the standard GP equation, which is we observe some kind of enhancement of these Kelvin waves. We observe that in the generalized GP equation, there's more energy that is injected in this case, and that the Kelvin wave spectrum is developed better than in the GP case. But on the other hand, for the circulation, this is not relevant because the Kelvin wave cascade is not relevant for the circulation, and in this regime we observe only the scaling of single vortices.
Do you think this is the effect of some presence of rotons?
Yes, I think so. Yes, actually, something that here in this bump here, which is maybe not very clear, but here there is a bump. It is related with the scale with the roton minimum, for example. So I think that Yes.
Okay, quite interesting. Thank you very much.
Welcome.
I think Wei had his hand up first.
Thanks for the nice talk, Nicolás. I have a similar question as Makoto. You used this generalized GP model, but did you tune the parameters so you can reproduce some key properties of liquid helium, say the speed of sound and dispersion in the phonon region, such and such?
Well, yes, we fitted the parameters in order to reproduce this same excitation spectrum and the same Rotom minimum. So yes, and that fixes you the speed of sound of the system. And yes, this is something that we did with the generalized. I mean, here you have a few parameters that you can fit to reproduce that.
What about surface tension?
Sorry, again?
What about surface tension?
Well, no, actually, we didn't consider that. We only studied this model to be able to reproduce the excitation spectrum of helium. I don't know, I would have to think about that, but I don't know how would that change in this system. So I would have to take a look at that, but yes, thank you. Thank you for the remark.
Okay, thanks.
Time for one quick question before we move on to Ollie's talk.
Yeah, just a quick one, if it is okay. Just to complement the Makoto's and Wei's questions, because you can remember what Natalia Belov did some time ago. She tried to fit the equation of state.
Yes.
Right, for helium. What about the equation of state? Does it in any way resemble what it is for helium, or?
Well, yes, actually, she tried to do that to reproduce the same, yes. And actually, this parameter is what it is important to reproduce the equation of state of the system. And we chose basically the same parameter that she used to reproduce the same.
All right.
The same system.
Okay. Thank you. Thank you.
You're welcome.
Mm-hmm.
Okay, well, thanks very much, Nicolás, particularly for fielding all those questions.
Okay, thank you very much.
So, Holly, do you want to try bringing your?
Yeah, sure.
So next up in our double headers, Holly Middleton-Spencer from Newcastle, who's going to be talking about vortex states within an expanding BEC.
Okay.
So, Holly, when you're ready.
Okay. Hi, as Andrew just said, my name is Holly, and I'm a PhD student at Newcastle, and my supervisors are Nick Parker, Luca Galantucci, and Carlo Berenghi. And today I'm going to be talking about expanding condensates and specifically vortices within them. So I'll start with a brief discussion of experimental methods in BECs, both in visualization of condensates and also of quantum turbulence, before moving on to the mathematics and computational models I use before going on to some results. So why do we need to study the expansion of condensates? So BECs in experiments are normally imaged using a method called absorption imaging, which usually relies on a laser being shone at the condensate, and on the other side, they image it, the resulting light that comes through. The issue, one of the issues with that is that the laser it's used, the wavelength of the laser is usually around on the same scale length as the healing length of the condensate. So things like vortices, sound waves, etc., can be difficult to visualize in a condensate if you keep the condensate trapped in its potential. So what many experimentalists do is they release the condensate and then take a few images. And many papers work on, papers I've read work on a few assumptions. For example, it's assumed that the core size, so the width of the vortex, as the condensate is expanding, the width of the vortex expands at a much quicker rate than the actual background condensate. And it's also assumed, which is important in, say, turbulence experiments, that when a condensate expands, whatever's going on, i.e. turbulence in the condensate, when you then release it to expand it, what's happening inside is effectively frozen. So what you're seeing after your time of flight image is what was going on in the condensate just before release. So we all see many papers on experimental quantum turbulence in both helium and BCs. Each of them has their own advantages and disadvantages. For example, helium, you can have a much larger range of scale lengths in the condensate in the system compared to BCs, whereas BCs are much more tunable than helium. And again, as I've just stated, the visualization in the BC is often with the time of flight imaging, whereas helium, for example, they use solid hydrogen imaging. One important factor of expansion of a BC, if you have an anisotropic, so say a cigar condensate, when you release it, it will invert its shape. However, in 2009, when the group of Vanderlei Bagnato first produced quantum turbulence within a condensate, they found that when it was expanding, they see what is called a self-similar expansion. So for this, this figure is from their paper. On the left is a normal condensate. You see it's quite, it's a cigar condensate, and when it expands, it inverts. However, on the right is their turbulence. So they have the same sort of shape condensate. And when it expands, you can notice two different things instantly. Again, the self-similar expansion, it's the ratio of the horizontal and vertical doesn't really change. And also it's expanding much quicker. So as Nicholas discussed earlier, if we can assume that BCs are weakly interacting and dilute, and if we assume that the temperature is 0, we can simply model the BC with a single wave function, and we use the Gross-Pityevsky equation to solve it. I use in my work harmonic oscillator units. This just means that I scale the time, the length, and the density by the trapping potential in R, so the radial direction of the condensate. And we use this potential here, where you can change the shape of the condensate using the trapping potential in Z. Here we assume that X and Y are R. If you make these assumptions, you can have 3 different shapes of condensate. On the left is our very simple spherical case. In the middle is a pancake, and on the right is a cigar. So that's the terminology I use. And again, we can make more assumptions, and assuming that the condensate is large enough and repulsive enough, we can make certain approximations, and we can actually model the density of the condensate using the Thomas Fermi profile, which is a parabola. And you can kind of define a radius. And you can actually use this Thomas Fermi approximation for density to actually gain a coupled second order ODE, which you can solve. And you can look at various things like dipole modes, monopole modes, so various oscillatory modes in condensates. And also you can model the shape of the expansion of the condensate. So if you look at, say, for example, spherical condensate here on the left, if you look at how the Thomas Fermi profile would behave in time if you released it from a condensate trap, you see that it simply expands out. This is the radius of the condensate, and you see that there are 2 kind of regimes. So there's, at first, the condensate will begin to accelerate out, and then it will spread out at a single speed. If we, for example, look at a cigar condensate, like the one in the middle here, When you release it, it will, as I've stated a couple of times already, it will begin to invert, and you'll see that there is you'll see that in this here. So I use a 3D GPU code where I simulate the expansion of condensates. Obviously, this has its difficulties at time, because not only have you've got to make sure the computational domain, for example, is large enough so that you can expand the condensate for a meaningful time. So I initially find my condensate by taking my Thomas Fermi profile, running that in what's called imaginary time, and that will find the ground state of the system. And when I want to induce simple vortices placed, I use Natalia Berloff's approximation for the weight function of a vortex. So this term in the square root is the density approximation, and then there's also a phase winding. And if you then run that again in imaginary time for a bit, you will then get a real vortex appear. So we begin by first looking at what happens to a single vortex system as it's expanding. And there have been a few works, especially in 2D, and so I began to look at it in 3D. So if you take a simple condensate, put a vortex along the Z direction, and we can interpolate the width of the vortex by, and I choose, for example, I quantify this width by saying, well, I'll call R0 the location in R where the density has fallen to 90% of the peak density of the condensate. And if I then expand that condensate and I measure both the width of the overall cloud and also the width of the vortex core as it's expanding, I can see the ratios. And so when I do this, I see that the assumption in papers that a vortex expands quicker than the background density is correct. This figure here is for different shapes of condensates. So when you have a vortex in a very anisotropic condensate, you will, and if the vortex is aligned along the smallest axis, then the vortex itself does expand much quicker than the condensate around it, which is good for imaging. If I then start to look at two vortex systems, as we know, when a vortex and anti-vortex come near each other, they will reconnect, and this is very important in terms of when we're discussing quantum turbulence. So if I set up a system here where there's a simple spherical condensate, a vortex, anti-vortex placed parallel to each other, and I put them at a distance which I call Z0. I can see the time of reconnection if I were just to leave a condensate sitting in as where it is, and what happens when I then instead expand this condensate. What happens to the vortices? Do they instantly stop reconnecting, or is it more complicated than that? So as we know, if you look at this top-down image, the vortices will approach each other and then they'll reconnect, and they'll also release some sound waves. So this is for a non-expanding case. The further away the two vortices, the longer it takes to reconnect, which makes sense. And if I then go and look at, if I then go and expand that condensate and measure the time of reconnection, I actually see that reconnections do not necessarily stop during expansion. And so the red line here is the time of reconnection for the expanding condensate, and you see that it stops here. I need to do a lot more work on this because it's stopping here. That could be that my computational domain is not, the time for reconnection will take much longer than I can simulate, or it could just be that these two vortices will never reconnect, and I'm looking at that further now. But looking at the results we have for the vortices that do reconnect during expansion, they follow this trend. So the expansion of the time for reconnection in the expanding case divided by the time of reconnection in the normal case is exactly the ratio of the healing length of the expanded state at that time divided by the initial healing length. And then we then go and look at, if we then, so that's work ongoing, so I didn't explain that well. So I then begin to look at what happens to many vortices within a condensate. So I've done quite a lot of playing around basically. And so if you take this Cigar condensate where it's twice as long as it is wide, and you put vortices in at a fixed distance away from each other and put them in so that the overall net circulation of the condensate is 0. Here is, for example, is the condensate with 8 vortices. And then, for example, this is another one with 48 vortices and many more. What happens to the size of the vortex of the condensate when it's expanding? And so I quantify the width of the condensate during expansion by using the integrated density, and I look for the value at which the density is 1/10 of the peak density of the system. And that's how I define the width. If we then expand many different simulations and look, we see that indeed, the more vortices you have in a system, the less the system inverts in time. So the ODE is, so this is the prediction for what happens to the ground state, and simulations do agree with that, the black line here. And then as you put more vortices in the system, the inversion happens less, which is very interesting because this means that the so-called self-similar expansion that's quoted quite often in literature, we cannot say that that is a signature of quantum turbulence. That has to be a signature that there are many vortices in the system. And the actual mechanism for the vortices holding, kind of pinning the sides of the condensate in place are still being investigated. I'm not entirely sure why it is that the vortices themselves hold the condensate in the shape it originally is. So in conclusion, we have verified that vortices expand much quicker than the background condensate. So expanding does help visualization and experiments for the vortices. Reconnections can still occur during expansion. And we have shown that vortex arrays actually, the vortices themselves actually greatly affect the expansion of a condensate, not necessarily the quantum turbulence. So that's me. Any questions?
Sorry, I'm speaking away, but I'm muted, aren't I?
That's all right.
Marvelous. Thanks very much, Holly, for another interesting talk. Callie, go, put me out my misery.
Hi, Holly. Thanks a lot
Hi.
for an interesting talk. I was wondering if you'd looked at all at the effect of different arrangements of vortices. I see that you quantified just for how many, but does it make any difference if they're ordered or disordered or?
So I deliberately looked at ordered ones, especially spaced out, because I didn't want them to reconnect in time, because I didn't want to, maybe the reconnections themselves kind of assisted in the pushing out the condensate. So I deliberately chose systems where the vortices were very set out in strict arrays spaced out. But yeah, that is something I'm doing now. So I'm looking at more disordered states and for example, expanding that, and also the same state, leaving that to evolve to get a more turbulenty system, and seeing the difference and expanding that and seeing the difference between the two. So yeah.
Okay, thank you.
Yeah, I was it's related, but I wondered if you had sort of a cloud of rings of very small radius, and that was left to expand. You know, is it something about having energy at scales of the order of the condensate that impacts the nature of its expansion?
Yeah, I was wondering that, whether it's the energies or the actual vortices themselves in the direction, but I'm not actually sure. So that's definitely something I am looking at.
Okay, thank you.
Because there are a few papers, for example, where they look at, so I don't know the term, sorry, I'm struggling to put it into words, like energy, bounds of energy which give different systems. So I was wondering if that was related to how they're expanding as well.
We have time for more questions before we wrap up. No, if there's no one else, then I'll thank Holly and Nicolás for their talks today.